How do you boil water? I mean, it sounds like the simplest question in the world, right? You grab a pot, you turn on the heat, you wait. But what if I told you that simple, everyday act becomes a totally mind-bending physics puzzle the second you leave Earth? Okay, let's get into it.
See, here on Earth, we know exactly what's going to happen. The water heats up evenly, bubbles form and float to the top, and steam comes off. It's predictable. But in space, in microgravity, all of that intuition just goes right out the window. The rules we count on, they just don't apply anymore. And what you're left with is a really fascinating mystery.
And the whole problem, it really boils down to two invisible forces that we never, ever think about when we're making a cup of tea: gravity and atmospheric pressure. They are the silent architects of the whole thing. Take them away, and well, everything changes. So let's take a look at how our everyday physics just completely breaks down, because up in orbit, what we think of as a simple chore, well, it turns into a serious experiment in thermodynamics.
Okay, so the first thing to go is convection. You know how on Earth you heat water from the bottom, and that warmer water gets less dense, so it rises, and then the cooler, denser water on top sinks down to take its place? That creates this constant churning, this current that heats the whole pot nice and evenly. Well, you guessed it, gravity is the engine that drives that whole process.
So without gravity, there is no up for the hot water to go to, and there's no down for the cold water to sink from. They just stay put. So if you try to heat a blob of water in space, all you do is create this tiny, superheated bubble of water right next to the heater, while the rest of it stays completely cold. It's not just inefficient, it's actually pretty dangerous.
All right, but let's say you do manage to make some steam. Now you've got problem number 2. Here on Earth, bubbles rise because of buoyancy. That's the upward push from the liquid around them, which, again, is an effect of gravity. In space, without that upward shove, bubbles have absolutely no reason to go anywhere. They just form and get stuck right where they are.
And this is where it gets really, really weird. This is a direct quote from NASA experiments on the International Space Station. Instead of a normal rolling boil, you get these bizarre, shimmering, pulsing orbs of vapor that are trapped inside a shell of liquid. They just float there, merging into one another. It's less like boiling water and more like some kind of strange alien life form.
So if our most basic physics has totally failed us, how do astronauts get a hot cup of coffee? Or, more importantly, how do they survive? Well, this is where some incredible engineering comes in to basically create a whole new reality.
And the stakes here are unbelievably high. I mean, trying to boil water in an open pot on a spacecraft would be a complete and utter disaster. You'd have these floating blobs of scalding hot water just drifting through a cabin that's filled with millions of dollars of incredibly sensitive electronics. Yeah, it's just not an option. To get around this, engineers developed some absolutely brilliant solutions. Astronauts use these sealed, pressure-regulated containers. They're basically super high-tech space kettles. They don't rely on gravity at all. Instead, they use things like forced circulation or special capillary pumps that use surface tension in really clever ways to move the water around and make sure it gets heated safely and evenly. And this kind of technology is about so much more than just creature comforts. The ability to control how liquids turn into gas and back again, that is absolutely fundamental for life support systems in space. In fact, check this out. The ISS's life support system. It's called ECLSS. It uses these exact principles of controlled evaporation and condensation to recycle an incredible 90% of all the water on board. And that's water from the crew's breath, their sweat, even their urine. So yeah, mastering boiling in space is really about mastering survival. And this all brings us to a much bigger point, because studying this one seemingly small problem in space actually teaches us some really profound lessons about our own planet and about our future out there in the cosmos. The research from these experiments has applications that go way beyond the ISS. It's helping us design better cooling systems for satellites, it's informing the design of future power systems, and of course, it's absolutely critical for engineering the habitats we're going to need to actually live on the Moon and Mars. And speaking of Mars, remember that other force, atmospheric pressure? Just look at the difference here. The atmosphere on Mars is so incredibly thin that water there boils at just 10 degrees Celsius. That's basically the temperature inside your fridge. You couldn't just step outside and boil water on Mars, it would instantly flash into vapor. Engineers have to plan for that in every single thing they design. And this brings us to a really beautiful idea. By taking gravity out of the equation, by removing all that noise, scientists in space can study the fundamental forces like heat transfer and surface tension in their absolute purest forms. It lets us refine our understanding of physics in ways that are just impossible down here on Earth, and that benefits countless technologies back home.
So, ultimately, what this all shows us is that gravity is so much more than just the thing that keeps our feet on the ground. It is a fundamental force of organization. It's a silent architect that creates order in the universe, shaping everything from the massive weather patterns on our planet right down to the simple, predictable way our kettle boils every single morning.
And that really leaves us with one last thought. We've just seen how taking gravity away completely upends one of the simplest things we know. So it makes you wonder, doesn't it? If gravity has this much control over something as mundane as boiling water, what other parts of our world, our biology, our very existence, does it secretly control?